Good afternoon, good morning, good evening to everyone who's joined today. Thank you all for joining. I'd like to introduce myself. My name's Sarah Chowdhury. I'm part of the Fritz Gyger sales team. Also, we have Selena Dallenbach, who's also part of our team, and Boris Maurer, the Certus Flex product manager, is also online as well for later on for questions. And a huge thank you and a huge welcome to Remco Winter from PPSC. So I'm just going to give a short introduction to Remco and the webinar. Remco holds a PhD in biochemistry and molecular enzymology from the University of Groningen and is a director of high throughput screening at Pivot Park Screening Centre, also known to many of us as PPSC in Oz. PPSC is a contract research organisation specialised in the field of early drug discovery assay development, lab automation, ultra-high throughput screening, µHTS, and hit-to-lead biological profiling. The title of our webinar today is Putting the U into µHTS, how assay development, dispensing and detection technologies can be used to perform drug discovery screens at 1536 well format consistently. Remco will share PPSC's latest developments, including their unique implementation of MS-based readouts and how they overcome the challenges on infrastructure and assay requirements to ensure the HTS remains an ultra class. So over to you, Remco. Thank you.
Thank you very much, Sarah. Hello, everyone, and welcome. Thank you for joining. Thanks for this opportunity to present here today. Indeed, putting the U into µHTS. I would like to start by first telling a little bit more about Pivot Park Screening Centre, where we're from and what we do. Our mission basically is the discovery of new medicines for a healthier society. Many of you are familiar with the drug discovery pipeline and timelines. We operate, as the schematic picture shows here, very much at the beginning of this timeline. And the target discovery, assay development, hit finding, where ultra high throughput screening, finding of hits for new targets, for novel targets, is one of the things we are very highly specialized in. As already mentioned, Pivot Park Screening Centre, we're a contract research organization, small company, around 30 people headcount, but we have a very strong, big pharma heritage. We originate, our roots go back to the well-known Dutch pharmaceutical company, Organon, and already in the mid-90s, high throughput screening, medium throughput screening was introduced, the infrastructure and screening campaigns. And the know-how in our people and the staff, some of the staff we have working for us now was already embedded and started then. Early in the 2000s, the infrastructure was expanded, ultra high throughput screening capacity was miniaturization was introduced with the acquisitions of Schering Plough and later by MSD. When the research and development was closed in Oz, when MSD left, Pivot Park Screening Centre started shortly afterwards as a small as a spin out with the infrastructure that was at that time still here, specializing really on ultra high throughput screening and assay development up to the present day. Of course, screening is one thing. You need to be able to measure something when you're screening. So assay development is also one of our core disciplines and specialties. We have a large team of very talented assay developers. And essentially for pretty much any target, we can develop an assay and miniaturize it to screen for. A large portion is, of course, for enzymes, but as you can see in this graph, in this pie chart, many other different targets can be catered to, and we have in our portfolio we can develop an assay for. I mentioned already miniaturization. 1536 wells well screening was of course highlighted in the title. Yeah, that's very much screening in 1536 well is really our bread and butter. It's a large portion of our assays, miniaturized. We develop them really to do them at this scale, to be able to get that ultra high throughput capacity, much less to a smaller degree in 384 well, which we can also do. Targets are screened against unique compound libraries. We have our own compound library, around 300,000 compounds, still a legacy of our time when we belonged to Organon. As part of the European Lead Factory Consortium, we also have access to a unique library of over 500,000, 500,000 compounds. For ultra-high throughput screening, and of course, as a contract research organization, whatever a client brings in from big pharma companies, commonly 200,000 up to 1 million plus compounds we can cater to, and we have that infrastructure. It's also, of course, possible because of the compound logistics, which I'll go into later, and handling and ultra-high throughput screening, and the automated data processing that goes along with that, which is highly important. Which we do, I need to stress, in real time, on the fly data analysis. Screening is one thing, primary screening, finding the initial hits. But of course, to confirm this, we also do a lot of active confirmation, deselection assays and orthogonal assays, to get worthwhile, meaningful hits afterwards. Following up from screening, of course, hit to lead profiling, the second, the subsequent steps. We have a number of tailored hit to lead profiling cascades. We commonly do dose response analysis, also structure activity relationships, also in an automated fashion. The next part of my presentation, I'd like to go into a bit more detail on the developments in our µHTS platform and how we keep it fit for future. I think this is a nice picture, a nice panoramic view of our µHTS platform in Oss. The automation system was built by High-Res Biosolutions, which we partner with here. You see here from the side view the yellow Staubli industrial robot arms and all the devices around these robots. Looking at it from a helicopter view, a schematic picture, the automation system we have in Oss, the PPSC, it's basically it's a 3-pod system, very simply put, 3 pods, 3 functions. Pod 1 is storage, pod 2 is dispense, and pod 3 is analyze, connected by a conveyor belt with a smaller robot depicted here in the center. Blue arrows is the sort of the general movement of 1536 well plates throughout the system. So we take these pods one by one and go into a little bit more detail on what they can do and how we keep them operating in tip-top shape. Pod 1, as I said, is compound storage, compound transfer. All the libraries are stored here under controlled conditions, nitrogen, temperature controlled, sealed plates. It can be desealed, resealed again. Transfer, they're very valuable compounds, of course. We don't have huge amounts. It's done acoustically via the echo acoustic handlers, of which we have several. If I show that in a more schematic format, we have redundancy in the system for backup, so we can continuously screen also, but also if we can do parallel tracks in the automation, transferring compound plates for the screening, but also reference plates for quality control, making quality control plates. Schematically depicted here, destination plates from source plates to destination plates. Of course, when you have a reference plate, you have less source plates. So as I said, we have several systems to make it, to keep it redundant, to keep it, make it go faster. In the case of breakdown, we can move in another system very rapidly. Of course, continuous monitoring is important. Things can still go wrong as they do, or the quality of the libraries sometimes we sometimes have to deal with is lower. There's a nice example here of an innovation we added to maintain a high quality. In this schematic picture here, as you can see, as the screen progressed after approximately plate 20, the signal to blank was that prime value had dropped dramatically. So basically the screen data is no longer reliable, can be used. Troubleshooting was performed and root cause analysis, and it became clear that water uptake in the echo causes this drop in quality, sometimes with the reference plate, depending on the type of screens. Were open for a longer period of time and they can attract water, leading to a less reliable so the DMSO content goes down, obviously, as the water content increases, leading to a less reliable transfer and inability to transfer accurately with the ecosystems we use. You see here at the edges already here, this was measured by an echo survey, and in time, progressively throughout the entire plate until it all didn't look very nice. So to identify which plates where this occurred, that this was in this case with the reference plate. As I said, it stays open for a longer period of time. The water attraction, you need to get rid of the water now. Many ways, possibilities to do this, and we developed a nice innovation to dry the reference source plates or compound libraries. Rather elegant, I have to say, and you may see elegant. I see a plastic box, and that's indeed the case, with holes drilled in it, and we can make it airtight, seal it airtight container with DMSO, pure DMSO in the plates, under nitrogen, flush it under pure nitrogen for several days, and then in this way getting rid of the water in the plates, the DMSO containing compound plates, and making sure that the level of DMSO goes back to what it should be to enable a good, accurate transfer. So yeah, basically a perfect marriage of low and high tech. Obviously, as the plate I showed a few slides back, if that occurs in a screen and the quality drops and we can't screen properly because the transfers don't occur accurately, solving this, fixing this through in a screen creates a lot of problems and also costs, more time, delays, lower quality. As you can see here, the reduction in costs, if you can, the cost savings you can gain if this is fixed is quite significant, up to 40,000 euros a year if you screen a lot. The investment in such a elegant solution, it's very low, 100 euros. So how often do you get a return on investment of over 400-fold? I would like to ask. So a nice example of sometimes seemingly simple solutions coupled to very high-tech devices maintain the daily operations and make sure we can really keep running ultra-high throughput screening continuously in a continual fashion. If we move on to the next pod, for a µHTS screen to be able to run continuously and fast, dispensing is really key, accurate dispensing. So in pod 2, we have a number of dispensers and incubators, plateway. When I say a number of dispensers, we have the Certus Flex, very good device for what we need. And yeah, as I said, a number, we have 5, and the number 6 is under consideration. We really need this amount. We can build it into our flexible pod system. Sometimes we can use them offline by removing the cards, which are from high risk. We can decouple them from the pod system to be able to, if you screen at 1536 well format, to get the flexibility, the system redundancy, and the capacity we need to maintain the screens at high speed. Still, and of course, there's a nice picture, but what does that look like in real life? So. A nice movie there, which I can always look at for a long time. But integrated in the system like this, we have, as I said, a large redundancy, 5 systems now. But it's one thing to do a screen, but to continuously screen and build a screen up, verify everything, make sure it's running properly, and break it down again, build it and clean it up, and then get it ready for the next screen. There's a lot of work that goes into that, and this turnaround time is very important in making sure that it goes as efficiently as possible. So we applied practices of lean 5S to the Certis dispensers in our system. We see one built in here. The robot is behind this gray safety door, so it's accessible to our robot operators. Yeah, I won't try to pronounce these Japanese terms, but basically sort, set in order, shine, standardize, and sustain is what the 5S means. And it's looking at your daily operations and identifying seemingly innocuous small items, not particularly sexy or high tech or anything like that, but by getting that really in order, maintaining that and doing it right every time can really save time, save money, increase your quality, and make things done every time in the same way. An example here is for the valves of the Certis. We use magnetic labels here, which we stick, which can be stuck on the side here, as you can see they're hanging there, to depict then what screen, what valves are being used. These are ones that have been verified, tested before a screen. We know these are the right ones that we're using, so we can go through before a screen starts, during screen days, that we're using the right valves, that there are no mistakes being made there. Also sorted and stored properly. And the same also applies to the reagent wash bottles here. They have tendency with the point a bit difficult to store upright. Here we made a little holder here with 3D printing so that they could be stored stored a little bit easier, a little bit neater, that we have the right ones collected together. So in this way, making for efficient operations. At the end of a screen, as I said, then it's done. But we're not about one screen. We're about doing lots of screens per year, as many as possible. Yeah. So, but the valves in the dispensers, also need to be cleaned properly. The integrity needs to be. We need to be 100% certain about them. Cleaning procedures are known, standardized protocols for that. But also checking afterwards that they are indeed properly clean. So with a microscope here, we can examine it and attach to a smartphone. So quite a simple system, a little 3D molded holder for a smartphone, so you can check. Is it properly? Are they clean? To take a picture and store that with the screen data. Lean or not, you have all your standard procedures, all your checklists, everything designed properly. Things can still go wrong. Things can still malfunction for whatever reason. You see here a picture, and obviously the colors are clear. Something somewhere, the right amounts were not added. This can happen at any time. It's something you always have to be very alert on. So dispensing is key, quality is king, I would like to say. You're only as good as your worst dispensing step. Seems obvious. To that end, we've also introduced one plateway. Second one is in the process. We hope within the next few months to implement another one. With the plateway, we can check, so really know, measure essentially, that the right amounts have been added. So we have all our procedures to trust our devices, to know that they operate properly, verified before we start, but also during the screen, that we can test that for every plate. I see here a schematic of how that's integrated small device built by High-Res Bio, that's available from High-Res Bio Solutions here. Basically takes a plate and measures it before and after every screen. It calculates the weight. You can see here we can monitor this in real time. This is from a particular parasite screen we did. There's a certain bandwidth which in it should be that we know, okay, for this particular screen, a certain amount has been added and the correct amounts have been dispensed. Here, this dropped over time we can get an alarm on that and an indication we need we need to take action and either stop the screen or move to another dispenser, change the valves, clean them, whatever. Of course, this entire procedure, also what I mentioned about quality, it starts before the screen already. Dispensing verification is, or for a particular assay during the assay development phase, is also imperative. This is shows this picture shows a cellular assay done together with the European Lead Factory Consortium, which was plated with Certiflex. It's a particular alpha screen assay, cellular assays. The percentage CV over the plate is respectable, I would say almost 8% for this assay. Also a combination of being cellular assay, also the type of detection technology that plays a role here. And a number of optimization steps we always perform. Verification with Tatrazine absorption measurement, where we measure the deviation from the average. We have certain targets on that have to be acceptable before we go ahead into screening. And before an assay is ready, declared screen ready. Some optimizations there. We run the Certis at a certain pressure, 0.3 bar, but for cell dispensing, it works better if we lower that cell pressure, cell dispensing pressure. I think here's a nice picture to show from a recent screen with one of our clients that the standardization and know-off really pays off. We have to miniaturize a screen, perform it at a larger scale, 1536 the cellular screen. Yeah, and I think the data shows is at prime and signal over blank ratio that this way of working, that despite the fact that we miniaturize, we can perform such a screen with more plates and more yielding more stable data. So we've had dispensing and compound storage at pod 3, the reading technologies where the analysis takes place. We have room for and a lot of different analysis technology devices. I have a list here. We can measure different types of fluorescence, FRET, luminescence, colorimetric. These devices built in, which we can also move around should it be necessary to other pods. We can also measure the Flipper Tetra fluorescence image based. Since relatively recently, the Rapiflex mass spectrometer from Bruker, which is also fully integrated in our system now. So I'd like to go into a little bit more detail on this particular analysis technology. Since 2020, we have this we've integrated in our µHTS system at PPSC, the Rapiflex Moldy pharma pills. You can see here it's also been built in, attached to one of these in the pods. One of the robot arm here it's fully automated, so everything's loaded in. It's quite a tall unit. We had to raise the ceiling somewhat to get it to fit in our building. Moldy is, of course, an MS which works with absorption desorption by laser. So you need a plate. The laser shoots the sample off the target plate. So we have a collaboration together with Analytic Jena, an automated spotter. So in 1536 well format, the samples are taken and spotted together with a matrix on the plates that can be then analyzed by the Moldy MS. So that the entire sample preparation and analysis is also automated and µHTS ready. Just before I go into a bit more detail on the particular assay and screen, we did, I think, nice to highlight some key benefits of the MALDI-TOF or mass spectrometry detection and ultra high throughput screening. It really is ultra high throughput, the speed, label free, so you're really measuring quite often the real compound of interest you can measure. You don't have expensive detection reagents are not required. expensive kits, fluorescently labeled compounds or substrates. There's a lower risk in general of readout technology interferences. Yeah, so as a result, less false positive hits. So quicker after your primary screen, do you get the information you want. Yeah, this means less effort for follow-up hit qualification, confirmation, and a wide variety of compounds can be detected. Small molecules, peptides, proteins, lipids. Yeah, so I'd like to go into a little bit more detail in the development of such an assay and what that takes, and how that compares to fluorescence assay, the more conventional assays, and the screening on the moldy. So if you look at the principle of an assay for ultra throughput screening based on mass spectrometry, a simple protocol, addition of enzyme and compound, incubation. We take a sample, we add a sample of stop buffer and a standard, internal standard necessary for the absolute quantification. And then a sample is taken of the assay mixture and prepared for on the moldy target plates. So there's matrix, assay mixture matrix. This is dried and then taken into the put into the Rapiflex. For absolute quantification, as you're looking at peak intensities, but to be able to really quantify how much of a product or substrate you have, you add a known amount of an internal standard. In general, something that is identical to your product, but an isotope of the product. Yeah, there's still as there is for every assay and for every technology, there's an amount of development and optimization that takes place. Yeah, it's very powerful technology, but there are always parameters that need optimization. You need to check the feasibility, optimization of the buffer, miniaturization, determination of kinetic parameters, linearity, tolerance, reference compounds, plate effects. So a similar amount of development as for a standard, maybe fluorescence intensity assay. And it is possible, just like with the fluorescence assay, to follow an absorbance or a Fritz assay, to follow a reaction in time by taking samples over time. So here you see T is 0, T is 30 minutes and 90 minutes. You see the peak of the substrate here. This is the mass over charge ratio. You see that slowly decreasing as the substrate is converted. And the nice thing about mass spectrometry is if there's no product yet, because you only just added the substrate at T is 0, you don't detect anything. There's no background signal when the product peak comes up. The standard here, an isotope of the product, of course, that should not be converted, and that remains at a standard steady signal. Yeah, of course, you get a quite standard looking trace of peak ratios, the amount converted over time. Yeah, so we developed a number of assays. We have an example of a mass spectrometry or fluorescence screen, so very similarly related substrates to really be able to compare the two and run them in parallel. With moldy TOF, so a substrate cleaved, so you see a mass difference which can be measured by the moldy TOF, and then a fluorescent labeled substrate where the fluorescent label is cleaved off and then becomes fluorescent, and you get a signal that you can follow. The protocol is, of course, the incubation. The reaction is very similar for moldy TOF. You add in a stop buffer, as mentioned before, standard, spotted onto a moldy target plate. For fluorescence, you can measure the sample directly in the Envision reader. And the robustness for both these screening protocols, Z prime was analyzed and found to be very acceptable. You see here quite a good prime and the peak ratio. The window of measurement was also good for both these assays. But when we do this initial phase of assay development and testing for our screens, we also test a set of compounds, the robustness set, which is a set of 262 unique different compounds, different classes. You see here how they're classified to test in your assay. This if you will get false positives. They shouldn't react. You want to know if there's something else in your reaction which will in your reaction mixture, which will react possibly also with all your target, your compound library, giving you a lot of false positive hits. Of course, the thought being that with their measure more specific, you will have less false positive hits. You can see that here. It's maybe a little bit difficult to see that, but it appears indeed that in multi-TOF analysis you get less false positive. Of course, it's nice for both screens. They're both very nice. The amount of false positives is low, so acceptable to screen or screening protocol. So in a different version of this graph, all the different robustness set compounds here. So the different classes. So 15 compounds had a false positive in both assays, fluorescence and MS. So you would say, irrespective of the detection technology, and most of these are redox active compounds. And as the assay buffer contains TSEP, a reducing agent, this is maybe could be expected that this occurs. But there are also 6 unique false positives, so 2.3% of the robustness set, that occur only in the fluorescence assay. You only see there, and 0 in the multi-TOF assay. So showing there a better specificity, a lower amount of false positives in the multi-TOF. So this would also indicate you to use this screening, this detection technology in your screen, you're likely to get less false positives, and in your primary screen, be able to move on quicker from your primary, from the hits you get there onto your next stage. All right, for the final.
Remco, can I just ask a quick question?
Of course.
We just had a question come through.
Yes.
So, in the comparison between the MS and fluorescence enzyme assays, you focused in assay quality in terms of Z prime, etc. But what about the pharmacology and sensitivity of both assay formats? Did you test a set of enzyme inhibitors to confirm that they worked equally, both formats, and according to their pharmacology?
That's a good question, and I don't know, to be sure. I would have to check with the experts. It's a very good question. A lot of work has gone in here. There's a lot of work behind here, and I'm really showing a taste of what was done. So I would have to get back to you on that one.
Okay, thanks.
Yes, continuing on. So comparing these in a multi-TOF based µHTS 1536 format screen was performed, really comparing the two together. So more than 25,000 compounds were screened to get this example. In the same target enzyme, you see here and compared in a single graph. So the very stable signal window and robustness for both screens. The signal window for the fluorescent-based assay is somewhat lower. There's more background, more deviation due to plate effects were observed. Sorry, even though it was still acceptable. So the indications were the multi-TOF assay really indicated better. Of course, question we often get, or we also ask each other internally, is how much can we screen for that? How fast? How many compounds? This screen was done 75,000 compounds in a day, 60 plates per day. But this is very, very rough. So it's a difficult question to answer. And really, I think bottom line is how much you can do, and how many. It really depends on the preparation time of the multi-target plate in the system. The fluorescent assay, it's the same one. There's also a very big bandwidth on how many you can do and how long you allow the system to run for, and stability of the reagent. So a very difficult question to give a single answer for. Yeah, like in the robustness set, when we did the screen on this compound library, follow-up of the actives was done that we got to determine, can we confirm them? Are they real actives? And it resulted, the results that came out, there was a lower false positive hit rate in the MALDI-TOF assay compared to the fluorescent-based assay. So yeah, quite a lot of numbers here, I realized, but the false positives, MALDI-TOF 22% versus 30% false positives in the fluorescent actives. So I think that shows a nice results. Very in many aspects a very similar confirmation of the results, but across the board, the MALDI-TOF performed somewhat better. Yeah, and follow-up activities, of course, active confirmation, orthogonal assays, deselection assays, and dose response curves also performed, which is something I've got here on the slide. So in duplicate, 7 points from the same active, done in with the different screening procedures, and they show similar PEC 50 values, which is, I think, a nice confirmation of the different technologies. And this is a somewhat, I guess, the same conclusion, but in a somewhat in a different way. I plotted the PEC 50s of these actives against each other versus the two different technologies, and yeah, you get a good alignment there. There were, of course, some that we could not analyze this for, but in general, this was possible and gave a very nice result. All right. Before I go to my final slide, take-home messages. Just a bit of a summary of this. This was one particular assay that I showed in a little bit more detail, some data. There's quite a lot of work has been done, the possibilities, quite a number of different types of assays that can be performed. And we've shown feasibility and proof of that in MALDI-TOF based, we can perform an ultra-high throughput screening also. The different target classes, peptidases, the proteases, phosphatases. So building up quite a lot of experience there. Yeah, it's a nice, I think, nice results to everyone who's been involved in this. So I think I wanted to just summarize with a simple slide with a few take-home messages. I think what I showed at the beginning with the dispensing and the quality control and standardized procedures, µHTS, I mean, it is fully automated by design, really high tech. Possibilities are amazing. The systems technologically, yeah, really nice what they can do, but yeah, often low tech solutions and yeah, just basic, simple, often quite labor intensive checklists and procedures are really essential to be able to screen in an ultra high throughput fashion, to be able to use it as a fully automated system. Time and time again, we prove that, we show that to ourselves, and we see the benefits in these in doing things in this way. And as to the integration of mass spectrometry as a detection technology, this offers great advantages, offers ultra high throughput and speed in drug discovery screens. Yeah, advantages being label free, less expensive detection reagents, less false positive hits, yeah, and can really detect a wide variety of compounds. So, of course, I need to thank a lot of people, pretty much everyone at PPSC. for helping me. And of course, I've been working at PPSC for an extremely long time, and for welcoming me there. I'd really like to thank Gyger and for allowing me to present to you all, and our partners at HighRes, Analytic Jena and Bruker, for the support with the MS and the automation. So thank you all. Sarah, back to you. I'm very open to questions. If I can't answer them, I will get back to you at a later stage.
That's great. Thank you so much. Thank you, Remco. Thank you for sharing you and your team's work at PPSC. We do have a few questions, so we'll go straight into them. Mm-hmm. Question: do you investigate or provide other MS-based readouts, for example, ESI-based, ECHO, MS, to cover mouldy, incompatible compounds, etc.?
Yeah, good question. Yeah, it's very much on the radar. We don't have that technology at the moment. But we are. I think we are looking at that, and we have collaborations with MS institutes. But yeah, we're really considering that. But at this point, it's not built into our system as capacity yet. No.
Okay. Oh, we've got a nice comment. Great presentation, thank you. What volumes do you ideally aim for in 1536?
It can vary, but it's 20, around 20 nanoliter, I believe, if I'm correct. Yeah, so yeah, but yeah, don't pin me down. It's a little bit variable sometimes. Yeah.
Okay. We have another question here. Can you screen bacterial growth inhibition?
Bacterial growth. So you, I would expect you mean the live cells, I guess.
I'm not sure what exactly. It was just a question. All these questions, but we'll collate, and then you know, Remco and his team will answer them, and then we'll share them with everyone as well. So if we can't answer them right now, we will do them. We've got
it depends on the readout. I guess we can get. We're looking very much at also cellular screens, cellular MS, also bacterial. Mm-hmm. Yeah. So. But also with other readouts, yeah, that depends very much on the readout. We have the we can do it.
He said absorbance OD 600. I mean,
that's a very simple basic measurement. Of course, I'm not sure how compatible with 1536 with the intensity that would be. So I'm, but I do know that there are lots of different ways to measure other reporters. So yeah.
Okay, we have another question. How do you QC your compound libraries?
Good. I don't quite understand the question. You mean that, like, something about the quality control of how we keep?
How do you QC your compound? And maybe the person who asked this question can elaborate. We'll just go on to another question. We've got, how do you routinely calibrate your valves during the µHTS?
During a µHTS campaign, it's done before and after each campaign. So during it's not. Then we make sure they're not used for other tests or anything like that. But we verify them, check them beforehand, clean them, verify them, and then throughout the assay, then they're just kept in the system or taken out and then used for when the next day comes. Yeah.
Another question. What is your typical price for screening 300,000 small molecules from your library to my target for binding?
I've got I'm not going to answer that one. I think it's too. No, then I'll get I'm not in charge of so no, that's
Okay, let's see if we.
I'll put them in touch with our business development.
Yeah.
They can, even if it's just a general question and they want to just get a general indication, they can give that. But I think they'll whack me if I say something now.
Let's have a look. Is there any other questions? Am I missing any? Oh, here we go. We've got another. Hold on, just bear with me. Oh, so back to the QC about how do you QC your compound libraries? He's elaborated. How do you know the compounds in your library are not degrading?
Yeah, okay, that's a good question. Yeah, it's not. It's something that's in our radar because we don't sort of routinely do like every measurement. We don't every time do like an MS type analysis or check on. We do that. We have done that at certain intervals, but it's sort of. We see it in. There's always QC, so we have a maximum. We know what to expect for certain compounds. So a subset we analyze, but the entire library checking the quality is not something we do. It's sort of, I guess, through time based on all the data we have, and we're monitoring all the screens that we see that the quality should be okay. But real definitive answer on okay is the content. We know that when we put it in there, it was 95% pure. Is it still 95, or is it now gone down to 88, for example? That's something we don't track in time.
Can one really dry DMSO or water mix from 80% DMSO to 95% DMSO under
sorry, repeat that, please.
Question: can one really dry DMSO or water, a DMSO water mix from 80% DMSO to 95% DMSO?
We can get pretty high. That we don't. Sometimes it's also we need to get high enough so that we can survey again with the echo. We know what the heck, because then it can determine what the DMSO content is with the ecosystems we use. I know there are now ecosystems available which can also go more lower and more aqueous solutions. But as long as we can measure that, then so we don't always have to go that high. But if we need to be able to know the quality, what's in there, so the system works well enough to dry well enough. Yeah.
Okay, just a couple of more questions. Loads are coming in now. Just a couple more. At what temperature do you store your compound library at?
It depends. When they're freshly prepared, they're stored at -20. But once we start using them, that cycle can only be once. So then we just store them actually at room temperature, sealed and under. There's a bit of nitrogen flow, and that's actually, in our experience, that's the best way of, and in the dark, the best way and most stable way of storing them.
Okay.
But we use these. Of course, these are used, so it's not like long term. So long term would be in the freezer, but then for the period we use it, it's okay.
Okay, just two more questions. For your aqueous solutions, do you have a problem with evaporation with these small volumes in the 1536?
It can be if it has to be done at for some reason at a higher temperature. But we try often to do things at room temperature, for example. You can see some of those plate effects was drying in from the end, and it also depends very much on how long are the incubation times, how long are the times, the pacing times through the system. So it really depends on the asset. So it's something we have plate effects and everything. We also have to analyze throughout a screen and setting up a screen. Yes.
Okay. Let's just have a look. Yeah, there's a couple more, but I think we're running out of time. So
yes.
Yeah, that was a lot. There was a lot of good questions there. So we'll end the session today. We'll end the webinar today. Just again, a huge thank you to everybody who joined. huge thank you for Remco for sharing and your time today as well, and all the people and the team at PPSC. You've been a huge support to us as well at Gyger, and we look forward to working with you even more over the next months and years. I'd like to also mention that all the questions, we'll collate them and we'll answer them. Lots of people are actually coming in just saying thank you, and it was a great presentation. Got one more question. Can we quickly answer that? What is your procedure with the quality control plates run in parallel with tested ones? How do you prepare them and keep them to ensure proper comparison? Maybe that's a question that we can ask.
Yeah.
Later.
Yeah, maybe. Yeah. It's, Okay. But again, yeah, thank you so much. It was great having you on today. And if you have any questions, if anyone has any further questions, please reach out to Remco and the guys at PPSC, and also reach out to us if you'd like more information. This session will be recorded and it will be sent out to everybody that registered. Thank you. Bye-bye.